recording for today. Okay, so today we are going to talk about the very last tutorial, which is your network security. So multimedia networking is like kind of removed from the syllabus this semester, so that's kind of a good thing because the material is actually quite many, although it's like quite shallow. But yeah, the more emphasis will be on the network security side. So for those who just came in, this tutorial uses cookies to enhance your experience, so please accept some of my cookies in front. But yeah, don't eat too much because if you eat too much, then you are just Google Chrome. Okay, so we are going to talk about network security. So this was a classic 2107 material. So for those who are in 2107, feel free to participate more. But yeah, today we are going to talk about network security. When we talk about network security, we kind of like want to talk about 4 key components that we want to maintain. First one is what we call the confidentiality. Confidential means that if it's addressed to you, only you can access it. No one else should be able to read that contents, right? Something like, for example, if you get your SingPass letter, right, no one else should be able to see what your code is. That is what we call confidentiality. Authentication means that if this letter happens to be coming from SingPass, you want to know that this is actually coming from the government. You don't want someone else to forge this kind of letter, right? So you want to authenticate whether this is actually an authentic letter. Then we have integrity. Integrity will actually ensure that the message is not altered. Same thing, you have your SingPass letter. You don't want your mailman to actually change your code. That is basically violating your integrity. Finally, availability means that all services must be accessible and available to users. So this is more in the case of, if you heard of the DDoS attacks. So DDoS is actually when you have like multiple like computers, right? Multiple hosts. Your program actually infects them so that they will all hit to like one single endpoint. So that endpoint itself in the server, it's kind of get like overused. Then it cannot serve anyone else. So then we said that that server is no longer available. So that is violating what we call the availability. Okay? Say for example, if you connect to google.com, if like everyone else connects to google.com, then technically it will not be accessible, right? So one single person, if that poor guy wants to Google something, he will not be able to do so. That is basically when availability is already compromised. Okay? Yeah. Then we are going to talk mainly about 3 important things today. Actually 4. Okay, so we are going to talk mainly about encryption, both using the symmetric key encryption and also the public key encryption, as well as we are going to see how digital signature works in your public key cryptography and a bit on hashing. So what do we mean by when we want to encrypt something? If you want to send a message to someone, if you just send it as it is, if someone passes by and then they see your letter, then they know what it is, right? So in a sense, you want to kind of code that message out. So only the other person that knows how to decode that will be able to read your whole message. So that's basically encryption. Encryption will ensure that only those that you authorize to read your message will be able to access. Okay? So there are 2 types of encryption process that we introduced in this module. First one is what we call the symmetric key cryptography. From the word symmetric itself, that means you can use the same key to both encode and decode. Okay? So think of it like when you have 2 people, both of them will agree on the same key. Then they will just, the one person will encrypt it using that key. The other person will already have the key, right? So can just decrypt that. Okay? So that's what we call the symmetric key cryptography. Important property here that you will see later on in the tutorials. If you encode a message using the symmetric key and use the same symmetric key to decode, then you will get back the original message. That is basically the key property of symmetric key. Okay, questions? Okay. Then now we have the public key cryptography, which is a bit more complicated. So when we have public key cryptography, every single host will now have 2 separate keys. So there will be a public key, which we denote by K+. Then we also have the private key, K-. Too excited. Okay, so as the name suggests, right, if this K+ will be publicly available, so technically as a host, you will be able to share this anywhere else. So in common practice, there's actually a database that stores public keys of separate hosts. So if you want to connect to hosts, then you can just connect to them. Or sometimes there's also like certification authorities also. But this private key, your K-, will not be shared outside of your host. So it's only kept to yourself, as the name suggests. So how does this work? the way it works is if you have a message, then you encrypt it using someone's public key. So for example, if I want to send a message to Janine, okay? If I want to send a message to Janine, right? Janine has her private key. I have access to Janine's public key, right? So what I do now is I will lock mine with Janine's public key, so that when this comes, only Janine will be able to access, because the private key is only to her. Okay? So basically, if I use someone's public key to encrypt, that person can use their private key to get back the original message. Questions? No? Okay. Yeah, then you also have the reverse part, which is your digital signature. So in digital signature, what we do is we encrypt some message with a private key, such that anyone with a public key is able to verify that you are the one actually sending it. Okay? So in this case, for example, if I send Janine a message, then I can encrypt this message with my private key. For Janine to verify, right, she can use my public key. If the message is actually the same, then she knows that it actually comes from me, because it's the correct public-private key combination. Okay? Questions? Confusing? Okay, maybe let's try to give I think this is kind of a confusing part between your encryption and digital signature. But let's try to imagine it this way. Okay? Suppose that we have two items, say for example, can I have a volunteer name? Someone? William. Okay. Say for example, this is William's mailbox, then this is my mailbox. Okay? Make sense? If I want to send a letter to William, if I just leave it in front of the mailbox, is that safe? No, because someone else, for example, Nathan will be able to check, open up, and then see the content, right? So I want this to be accessible only to William. Okay? So then we have a concept of what we call the mailboxes, right? Okay, in a common mailbox, say in Singaporean post boxes, right, there will be a slot that you can fill in your message, and then there will be a slot for you to actually open, right, the key. The key is only to you, but everyone else can actually put the letters inside. Make sense? Okay, so how do I send a message to William without anyone opening it? Then logically speaking, when I prepare my letter, right, say for example this is my letter, then my letter I can just put it directly inside the mailbox. So when I address it inside here, technically I'm encrypting it with the public key. Because by then, no one else can access. Only William, who has the private key, will be able to open this. Make sense? Okay? So on William's side, when he wants to open this, then he can just use his private key, then we'll be able to access all the message. That is what we call encryption. My goal now is to ensure that no one else will be able to access this letter. Okay? Clear? Now, reverse side. When I send this letter, how do I make sure that only I can send this letter? How do I make sure that this letter is actually from me, not from someone else? Signature? Someone else can write my own signature. I tell you this is my signature, for example. If this is my signature, someone else can just copy. Can forge, right? If I put my name, can forge also.
Key?
What key?
Like you can only you have the key that can open up the mailbox.
Yeah, this is where it gets interesting. So if I want to tell William that this is actually me, what I do is I insert my key. Okay? Inside the letter, I append, say for example, my actual key, I put inside. So how does William verify this? When he receives the letter, right, it will be a combination of the actual message and my private key. Right, Jason's private key. How does he verify this? He can just use this key, check if my mailbox actually opens. Then you know that this is actually from me. Okay, that is kind of the logic here. So, rule of thumb, when you want to send to someone, in order to encrypt this message so that someone else cannot access, you encrypt with the recipient's public key so that the recipient can just decode with their private key. But in order to verify your authenticity, then you will have to encrypt some form of a message. Usually we use the hash digest. So we encrypt it with your private key so that everyone else can just verify it against your public key. So it's actually together in a sense. That's your encryption and digital signature. By using your public-private key, technically no one else will be able to forge in a sense. Unless your private key is compromised, of course. Any questions? No? Okay. Yeah, now let's go to the tutorial questions itself. So for question 1a, we want to use the substitution cipher shown in lecture 10 to encode this message. Has anyone tried this? Anyone would like to try? So it's easy. Yeah. Okay, I think that one is correct. Yeah, so we just match the T here. T will go to U, A, S, I, then all the way down. Okay, yeah, so I think it should be correct. Questions on this? This one is, I think, some primary school stuff that you usually do with your friends, right? Yeah. Same goes with if you want to decode the message, then all you do is to just compare it against the one in the bottom. So P corresponds to P on the original message. C in the encrypted one corresponds to corresponds to E, then all the way until you actually get the result. Okay? Questions? Easy, right? Okay. Now let's move on to the second question. The second question is actually corresponding to how we compare the kind of like the requirements of both symmetric key and also public key encryption. So suppose that we have n people who wants to communicate with n-1 other people. And then all communication between any two people is visible to all others, but no other person should be able to decode their communication. The question now is, if we use symmetric key encryption, how many keys are required in total? Let's take, say, if we have two people want to communicate with each other, how many keys do you need? One, right? Because one symmetric key can communicate between two people. So yeah, this is basically one symmetric key for two separate hosts. How about three? If three people wants to communicate, two, three? Who says two? Says three? Why is it three? It's a triangle, right? Yeah. So you kind of see that if you have three people, then you put like all three people here, then you see how many links you need, right? Each link will need one specific symmetric key. Or rather, we usually call it the session key also. Yeah. So each link would be one KS. Now what if you go to 4? If you go to 4, right? This is your first host, second host, third host, fourth host. Now this can connect to 3 separate hosts. This one will connect to 2 others, this one will connect to 1 other. Total here you will need 1, 2, 3, 4, 5, 6 symmetric keys. So what if you have n people? N minus 1 divided by 2, what? Use pattern. Yeah, this one is correct. So in the end, this is actually a complete graph. And in a complete graph, you can kind of do lots of different things. If you consider, for example, each host can connect to n minus 1 different hosts, so you multiply by n different hosts, but you consider that a connection between A to B is same thing as B to A, so I divide this by 2. That's one way to visualize that. Another way is, say, each of these 4 people, you want to see how many possible links can you make, right? So you take combination with regard to 2. So basically n choose 2. Then you will get this n times n minus 1 over 2. Okay? So that is under the case that we use symmetric key encryption. Any questions? Okay. Now what about if we use public key encryption instead? What would happen?
N keys, 2n.
2n? Why is it 2n?
N public and private.
Okay. Yeah. So if you use public key encryption, we will see that if in the case that 2 hosts are trying to communicate, each host will now have one public key, one private key. Right? So if you want to communicate with 2 hosts, now you need 4 separate keys. But if you go to 3 hosts, now you need 6 keys. If you go to 4 hosts, then you will need 8 keys. So it's only It's only dependent on how many hosts are there. Each of them will possess 2 keys. Then you can communicate with every other person. Okay? So this is a public key encryption process. So under a public key encryption, number of keys needed is simply how many people are trying to communicate times each of them will possess 2 keys, one public, one private. So that is your public key encryption. So you will see that actually when it already exceeds like n equals to 5, your public key actually requires less keys. That is why in a modern network we try to use public key also. Because imagine 1 million, right? You multiply this is n squared already. Yeah. So that's where your 2040 knowledge comes in, right? Polynomial, runtime versus linear. Yeah. So that is your public key encryption. Any questions? No? Okay. Yeah. Now question 3. Question 3 is actually a bit about how BitTorrent works. So let's try to see the question here. It's a bit long. So in the BitTorrent protocol, we have a seed that breaks file into blocks. Then the peers redistribute the blocks to each other. Then without any protection, an attacker can easily wreak havoc in the torrent by masquerading as a benevolent peer, then sending bogus blocks to a small subset of peers. So we want to find a method that is able to verify the integrity of a block such that it doesn't redistribute bogus blocks. So let me just give a bit of a primer on how your BitTorrent works, right? Anyone knows BitTorrent? BitTorrent knows, right? Knows, okay. Yeah, so how does BitTorrent work? Has anyone tried downloading from BitTorrent? What do you download? Okay, yeah, so if you try to download from BitTorrent, right, I think if you try to see the interface, what happens is actually, it will tell you like how many separate chunks it tries to download, then which host is it trying to contact. So this is one of the separate protocols, what we call the peer-to-peer distribution. What it means is, usually if you try to hit from certain endpoint, there will be only one single server, right, that will contain your files. So I want to hit, say, 1 gigabyte of files, then it will just be, this server will be the one returning me 1 gigabyte. Okay? But how BitTorrent works is, say for example, I have this 1 gigabyte file. This 1 gigabyte is going to be split into very, very small chunks. Okay? So these chunks will actually be stored into separate servers in a sense. And then each of them will actually be kind of like distributed alongside. So this is where it actually like the movement is a bit unpredictable sometimes. But it's kind of what we call the peer-to-peer, because like every single host inside will actually store something, then they just redistribute to each other. So it's not really a client to server communication, but rather it's like client to client in a sense. So for example, if I want to reconstruct this file, then all I need to do is to just obtain what are the addresses of each of the chunks that I want to get. Then I get directly from them. Usually that's what we do. Okay? So there is usually this file which we call the torrent file. The torrent file is like kind of the main source that you will actually refer to. So we want to see how do we actually verify the integrity of the files that you obtain from the torrent. How does it work? So assumes that when a peer joins a torrent, it gets a .torrent file from a trusted source. Okay, so this is actually the key point. What does the torrent file contain? Say for example this file, once I see it out, it will be in separate blocks. Then the blocks will be shared. For each of the block, there is going to be some hash value that is computed. So this hash value is basically the digest of that certain block. Okay, so separate chunks, each chunk will have the hash value. So what does this hash value do? The hash value are going to be combined. This is actually in the torrent file. Okay, so each blocks will have their hashes. The hashes are compiled together into one single torrent file. Okay, clear on this? Now, how do you compare this? In the case that I retrieve from, say for example, these 5 separate peers, then my block 2 comes in. If I want to check whether this block 2 is actually from a trusted source, all I need to do is to just compare it against the hash. So I hash this block, then I check whether the hashes are actually similar. Okay, that is how BitTorrent actually works for now. Questions? Although there will be more complicated stuff, of course. But this is a rough overview. So actually, I think I missed out on my review slides. But how is hashing different from encryption? This is important to know.
It's one way.
One way?
Hashing is only one way.
Why is it one way?
From the address, you cannot get back the input to the hash function.
Okay, so if you have like say a message, then you hash this, you cannot reconstruct this back. Okay, yeah, this is actually true. So if you cannot reconstruct it, why do we need hash in the first place?
It's for everyone to publicly verify the integrity of file.
That's one way. The other way is because hashing is fast. Compared to you do encryption, right? Encryption to actually determine what kind of, say for example, the public key, private key values, that's actually quite slow. Because lots and lots of restrictions are supposed to be there. In order for it to actually be reconstructible, and also for it to be like, you don't want people to be able to forge your keys, right? So in that case, then there are lots of considerations to be plugged inside. I think in the lecture they discuss like a short form of the RSA values, right? But in practice you will use like very very large numbers, and even in practice you don't use RSA because RSA was broken already. Yeah, there's like say elliptic cryptography. There's also like the SHA. Hey, SHA is a hash. Never mind. Yeah, there's like elliptic cryptography that's used in GitHub. I will show you later also. Yeah, so the way that hash is used is because it's fast. That's actually the main reason. But it's important to note that the reason why hash cannot be returned because it's not a 1-1 function. So many separate items, right? Because your hash value is quite small. The hash value is quite small, right? So in the end, this is kind of like, I forgot is it surjective or injective function. 1, 2, 3, 1. Yeah, but anyways, it's more like you have a huge domain that can map to the same small pointer here. So that is why hashing cannot be returned back. So this actually introduces some kind of this also introduces some kind of a vulnerability, right? In the sense that if I'm able to produce some other file that has the same hash, technically you will not be able to distinguish whether these two are different files. That's actually what we call like, I think, I forgot the exact term. Those who are taking security can remind me. I think there's like some kind of if you have an image of the same file, then there's like some attack there. Okay, other one. Okay, any questions? No? Okay. Yeah. So for this case, then technically if the hash matches, then we assume it's error-free because small probability for it to be corrupted. But of course, if you are able to match this hash, then yeah, boom. Okay, so hashing is actually quite a common practice. If you try to download, say like some folders, right? Usually they will tell you also what is their MD5 or SHA1 hash. All this is actually for you to be able to verify whether the file itself is actually provided by them. Because it's possible that, for example, if I'm on the attacker side, right? If I'm able to hack this website, then I change the link to download from somewhere else, then you will not be able to verify whether this is actually from them or not. That's why they try to attach the hashes. So once you download, you check some, you check if the hash matches, then you know it's correct. Unless, of course, if the attacker changes this also, then you have no idea. Okay? Questions on this? Okay, if no questions now, let's move on to the last one. This one I think will take some time. So the last part is actually, we are trying to see how encryption works in I think in an orchestra fashion, because we try to see how both the digital signature encryption and the symmetric key works together. Okay, so here we want to see how Alice will be able to send a secure email message to Bob, but we want to ensure both the confidentiality and integrity. So Alice does the following steps. Can I understand this? Okay. Yeah, so I prepared a very English term base. This is basically what it's trying to do. Say for example, I have a message, right? What I'm doing here is I'm trying to hash this message first. Whatever the hash value, I will encrypt it with Alice's private key. So what do you call this? After you encrypt with the private key, what specific type do you call this? Encryption or digital signature? This one should be signature, right? Because it is encrypted with the sender's private key. So someone else who has the public key can verify that it's actually from that sender. So this is actually the digital signature. Now this digital signature is going to be appended by the original message. So now you have like a digital signature message combo. This item, the whole combination of this concatenation, right, will be encrypted by what we call the session key. Then will be sent to Bob. But the problem is, the problem here is, both of them will have to agree on the session key. I cannot just simply send the session key. I will tell, for example, I will tell William, okay William, now we are going to talk with this key. Everyone else in the room knows, right, what key we are using. So there has to be a secure way to set this session key also. Since we are using the same medium to share, then likely you will have to encrypt the session key also. That's why the session key is here, encrypted by Bob's public key, you append it. Then the entire chunk of message is what you send to Bob. Okay, questions? Okay, yeah. So don't be don't be bamboozled by the mathematical notation. This actually tells you like if you have this function, that means you either encrypt or decrypt. Then this plus for the current case is an appending item. It's a concatenation. So for for security people, important to see that for this module, the way we put the plus sign, this one is for concatenation. Because most modules will use this as XOR. So take note of this also. Questions on how it works? Clear? Now we want to see if Bob receives that whole chunk of message, how do you verify that this message is from Alice? Can everyone visualize the message already? Any questions? No? Okay. So so just now was how we visualize the process, right? But now let's actually see how the message actually looks like. Okay, if you see the tutorial file, you will see that the message provided is actually, never mind. Yeah, you will see there's a long chunk of math stuff, right? That's actually the whole message, which I will elaborate soon. But if I want to verify that this message comes from Alice, how do I verify that? How do I verify the confidentiality, and how do I ensure the confidentiality and verify its integrity? Confidentiality is by encryption, right? Okay. Then, how else do I check whether it's actually from Alice, authenticity? And how do I check whether the message has not been tampered? That's two things. Signature is to ensure what? Authenticity. Okay? So this signature is used to verify that it actually comes from Alice, not from someone else. Okay, that's the signature. How if I want to check whether someone else has made changes to this message or not? That's where we compare it against the hash. That is to ensure the integrity of the whole message, whether someone else has changed the message or not. Okay, so two goals here. First goal is we want to extract the hash and extract the message, such that if I apply the hash here, I'm able to check whether the message has been changed or not. Okay, that's the first goal. Second goal is I want to be able to extract the digital signature also, such that when I verify it against Alice's public key, I'm able to retrieve back the original message. If I'm able to reconstruct the original message, then I know that it's actually from Alice. Okay? Questions? These are the two goals that we want to have. Now, how do we achieve these goals? That's where we have to actually look into how the message looks like. So this is the entire message. You will see that this is actually the result of the pipeline, right? Okay? I color-coded them so that it's easier to see. But this is provided in your tutorial. What happens here is, basically, I have the hash of the message just now on the top side. I hash it. Then I encrypt with Alice's private key. I will append it with the message. And then this entire thing is encrypted in the session key. Okay? Then afterwards, my session key is again encrypted in Bob's public key so that Bob is able to obtain the session key. Okay? All this is a concatenation. So this is the entire whole message. Of course, encryption is basically you change the whole bits, right? But in this case, so it's easier to see, I put them as logs. Okay? Questions on this? Can visualize, right? This is how your message looks like. So our goal now is we want to extract this item so I can verify Alice's public key, with Alice's public key. Then I want to extract the hash also so I can verify the message and the hash. That's my goal now. So as a child, of course, what you do is you try to break things. Okay, so here, what we want to break first is we see that this is a concatenation. Usually in practice, we already know how many bits are there when you append something. Okay, so by setting like set number of bits, you'll be able to know which part is actually the first one, which part is actually the second one. So first we split the concatenation. Once we split it, now we have two separate messages. One is your encrypted in session key. Other message is the one that is encrypted in the public key. What do we do next?
Take the session.
How do we take the session key?
Unblock using Bob 6.
Exactly. So this part, Bob already knows his private key, right? So Bob is able to check this. Someone else will not be able to open this. Okay? So next step is we want to get the session key. We use Bob's private key. You open this, we decrypt, right? So if you recall this notation, if you use Bob's private key to decrypt something that's encrypted in Bob's public key, then you will be able to extract the original message. That's where the math comes in. Okay? So message encrypted with Bob's public key can be decrypted with Bob's private key. Then you will be able to obtain the original session key. Questions? Okay? Remember the math, KS will give you the original message. KA plus, KA minus will give you original message. KA minus, KA plus will also give the original message. Just 3 things to memorize. Okay? Now once you get the session key, what do you do?
Use the session key and decrypt the data.
Okay, so you use the session key. You want to decrypt this data. So you apply this KS to this KS again. The result is going to be just whatever is inside. Okay? So once you unlock that, once you decrypt, now you have these two separate messages, which is just the concatenation of your message M with the H encrypted in Alice's private key. Any questions? Clear? Correct? Now what do you do?
Speed them or ladders now.
Split them again. Okay.
Then use Alice public key to verify the hash coherence.
Okay, so now we use Alice's public key in order to decrypt this. Okay? Since this is Bob, right? Bob has access to the public key, but Bob doesn't have access to Alice's private key. So we use Alice's public key to open this. We see that if the case that we are able to get the correct hash, right, then it's actually written by Alice lah. Or else then this should be a wrong item. Okay? So that's how we verify the authenticity in this case. So if I apply this KA, if this is encrypted with KA minus, if I decrypt with KA plus, this should return me the original message. Okay? That's how we verify your digital signature. Questions? No? So now we got the HM. What do we do last?
Hash against the message.
Exactly. So we just hash this message, we compare, see if they're the same. If not the same, then someone else has tampered. If they are the same, although we don't have guarantee that someone else has tampered, but low chance of it happening. If you choose the correct hash, of course. You choose a broken hash that hashes based on 0 or 1 only, then yeah, that one your problem. Okay?
How does Bob know which hash Alice is using?
Usually they will have to agree first. Yeah, but hash function is not a secret. So if you tell people that, okay, I'm going to use MD5, it's fine. Because usually it's hard to reconstruct back. The only thing that should be kept secret is your keys. Hash, everyone can know. That's why like even all the messages that if you want to download, right, they will tell you the checksum. They will tell you what kind of hash they use also so you can verify it against. Yeah, I think for this question they didn't specify, but usually it has to be agreeable upon both sides.
So if we're using say encryption to make sure the message is secure, then what's the point of the hash? What's the point of the hash if there's encryption on top of it?
Okay, so in a sense, encryption will ensure that no one else will be able to check the code. Okay? No one else will be able to check the code. So something like, say for example, how do I say this? Okay, say for example this thing. I will tell Janine, hello world. Okay? Then our code is we try to plus one letter. So what I will send to Jenny is going to be IFMMP, yeah, whatever this comes after lah. Okay, ISTME. So this is what I sent to Jenny. Okay, why do I send this? So that if Winston comes in, he will not be able to know what this is. That is encryption. Okay, so why do we still need the hash? If Winston comes in, he erases one of these to be Q. That's why we need the hash. The hash is there to ensure that someone else doesn't modify the message. Because what you see after encryption doesn't mean that it's locking. But encryption means that you are changing it so that someone else, when they see it, they should not be able to directly know what the message is. But doesn't mean that they cannot change the message. That's why hash is needed. Okay? Clear on this? That's the answer?
Yeah.
Okay.
And they can't change the hash. And they can't change the hash message.
The hash message, I mean they can, yes. They can, but if you hash based on this, right, usually it will go to a separate hash item. Hash is not linear, per se. So I cannot just say like, okay, this is one step, then I can just plus one to the hash or something. Doesn't work that way. That's why even your CRC can be used as a hash also sometimes. That's why it comes in. Okay. That's why one of the challenges is like how you are able to create better hash functions. Something that is not predictable that much. Okay. Clear on this? Okay. So there's another approach that we can do also. If you don't want to visualize the message, then you can also see from the whole pipeline. Then you can kind of reverse the process, right? So say for example, I start from the end here. What I do now is I want to obtain these items, right? Okay? So if I'm from the box side, then all I need to do is to just reverse the process. First one is I want to go this path, but this path is encrypted with the session key. So I will have to extract the session key first from here. But this one is encrypted with box public key. So I do is, I reverse this. Step 1, I use box private key to decrypt, right? Then I will get the session key KS. Next step is I go to this side. This side is encrypted with the session key, so I will decrypt with the session key. That's the second step, I reverse this process. Now I got the concatenation of your message with the hash and the private key. Okay? So up to this point, all I need to do now is to just separate out. Then I use Alice's public key to decrypt the hash value. Then I just match the hashes together. That's how I reverse the process if you want to see it that way. Okay? So two ways to approach this question. One is you can visualize how the message works. Or the second way is you can kind of reverse the entire pipeline. Questions? No? Okay, right? Usually this will be in the finals because it's a fun question to ask you about. At least for me, I like these kind of questions. Not just trivia, it's more like logical in a sense.
Is the flow the same, like for this model? Like, how is the entire flow the same?
For everything? No, this one is for this question only.
Only
This one is for this question. Then say if you want to change something else, then it's possible also. So need to understand the three key properties. Symmetric will give you the original message. Public key, private, public will give you the same message. Okay? That's the important thing to note. Questions? No? Okay. Follow up. Why do we need the session key? Can we remove this part and encrypt this with box public key instead? Why do we need the session key in the first place?
Does it have to do with like removing authorization? So it's like you only have access for that session?
More like why do you need one thing for that session itself? You can use the public key anytime, right?
less efficient.
Why is it less efficient?
Public key cryptography is less efficient.
Why is it?
Because you need to do all the modulo stuff.
Yeah. So public key and private key, as what it says, like public key is something that's publicly available, whereas symmetric key is something that's agreed upon between two hosts. So naturally, you want to make sure that this is as secure as possible. Naturally, okay? So that's why when you take your generator function, right, you will see that if you look through like all the cryptography papers, they will take really, really large values because they want to ensure that this is very hard to be cracked. So that's a public key, private key. So what is the session key used? For this current item, actually it's a bit irrelevant because you see that it's only sent a message once, right? But in common practice, what you do is you usually like try to send over the session key that's encrypted with someone else's public key. Because your public key encryption is much slower compared to your session key. Session key, one single key, small one is fine as long as someone else seeing this will not be able to depict, right? So it doesn't have to be that complex in a sense. So usually your public key cryptography is actually much more complex. So it will be slower. Such that if you want to contact with the host, right, if you are going to send multiple messages, the common practice is you send the first session key together. So after that, all the other messages can just be sent over with the same session key. That will be much faster for communicating. Okay?
So could you repeat the reason why public and private is more expensive?
The way that they structure the keys are actually like going to be something that as much as possible unbreakable. So the choices of values are more intrinsic per se, more sophisticated. Yeah. You can try counting the RSA values also. Yeah. So even in I think like last year's exam they tell you to compute like the P and the Q for the RSA, I think. They ask you to compute that in the exam. But the values that they test in the exam are smaller. Say for example 17, 19, 21, 23, something like that. But if you go to like actual values, right, they will take like really, really large numbers. Say like usually goes to like billions and items. Because they don't want it to be easily cracked, right, in a sense. Questions? No? Okay. Okay. If no questions then, actually that is it for this tutorial. Before that, right, in case that y'all haven't, for those who come late, for those who come late, please accept my cookies at front. This tutorial uses cookies to enhance your experience. So yeah, please accept some of my cookies. I brought for my other class also, so please, if y'all have taken once, can take twice. I think the class today is a bit small. Don't leave first because I will take attendance. Okay, but before that, before that, next week is a reading week. Since I don't have that much finals, I'm planning to hold one more consultation session. But in case that y'all want like any one-on-one consultation, please feel free to book through my Calendly link lah. Okay. But anyways, thank you very much for this semester. It was a very great learning experience. In case that y'all can provide me some improvements, teaching feedback is due next week, 27th. So can help fill in so that I can improve my teaching lah. Since I taught this for 2 semesters also, I want to see how I can improve if I teach this for next semester again. Plus, you get good karma, important for your finals. And yeah, you also get free moderate points. Yeah, but thank you very much for this semester. It was a very great learning experience. I hope you all enjoyed the classes. Sorry if there are like lots of different bumps. But maybe if we could take a class photo together. Okay. Because I taught for 4 semesters. The first 2 semesters I forgot to take a photo. How should we take? Can I timer this? Never mind. I'm bad at selfies. Anyone can selfie? Winston, you help selfie.
I grabbed someone from outside without Twitter before you. No.
No one. Long hands, anyone? Michael, I have. Yeah. Yeah, then if you have any questions, feel free to ask me. I'm free on the reading week. After exams, if you want to ask me anything about CS, feel free also. Don't want to ask me about CS, feel free. You ask me about how to find a girlfriend, I cannot help that one. Yeah, but okay. Thank you very much, guys. Let me just take a very quick attendance for today. I think lots of people are missing. But Alina, here. Amos? No? Chen Xun? Cheng Hong? Galen? Here. Jason, not here. Jiao? Joshua? Joshua here. Okay, yeah. Then Kristen here. Lyndon here. Why cannot we keep it? Michiel? Moonhee? Moonhee not here. Nathan here. Rachel? Tiffany? William? Winston? Here. Xavier? Xavier not here. Iye? Chanya? Okay. Anyone from T13? No, okay. Yeah. Then, yeah, that's it for today. Thank you very much, guys. Don't forget to fill the feedback. And all the best for your finals. Thank you.
Enggak, habisin 5. Habisin. Ya. Tapi pas sudah kerja ya.